We will talk about the ways to design the complementary CMOS circuits. So, understand, to implement any Boolean equation as a VLSI circuit, we need to use transistors, and the configuration what we are going to use now is called as complementary CMOS. To design the logic will be, or to implement the logic, will be using this style of design called as complementary CMOS. And we have already seen the inverter in the previous video, where we will be having one PMOS in the pull-up network and one NMOS in the pull-down network. We will be combining these two, and we will call this as our input, and this is nothing but our output. Source of the NMOS, as you know, it should always be pulled down, that is grounded, and source of PMOS, it should also always be pulled up, which is nothing but the VDD. It should be connected to 5 volt, right? Okay, now I will tell you some tricks in order to design, or in order to convert any Boolean equation into a complementary CMOS circuit, right? Okay, so the first thing what we have to understand is, in the design of complementary CMOS, we always have two different networks. One is called as the pull-up network, and another one will be called as pull-down network, right? And the source, all the source terminals of the pull-down network must be connected to the ground. If that is the case, that means pull-down network will always consist of NMOS transistors, and pull-up network will be consisting of only PMOS transistors, right? And in between them there is a node which is common to both pull-up networks and pull-down networks, that is gonna be acting as the output node, which is nothing but the output node, right? And whatever inputs you are giving to the pull down network, let us say input 1, input 2, input 3, it depends on the number of transistors and also the logic. For example, when you want to implement a 2 input NAND gate, the logic is actually y equal to a and b the whole bar, right? So in that case you need 2 inputs. Likewise, so whatever inputs you are giving to the pull down network, those inputs must be given to pull up network also, right? That is how the design should go on. So this is the basic structure of any complementary CMOS circuit. Okay, so there is a pull down network and pull up network, and output should be taken to the central node, and the inputs must be given like this. Here in complementary CMOS inverter, this is the CMOS inverter circuit. If you have observed, we have attained all these, right? So there is an NMOS in the pull down network, and there is a PMOS circuit or PMOS transistor in the pull up network. And as you can see, the input is given to both the transistors. As I already mentioned, the inputs, the same inputs must be given to both pull down and pull up, right? So here also the input is given to both the transistors, and the output is taken from the common node, right? Common node between the pull down network and the pull up network. That's how CMOS works, complementary CMOS, right? Okay, now I'll tell you one more trick in order to draw the pull down network and pull up network. The first thing to remember here is, pull down network or pull up network and pull down network are dual to each other. What do I mean by this duality? I'll explain in a while, don't worry, it is simple to understand. Now if I take a pull down network, and if I take two transistors, if I draw two transistors in series, and let us make one control signal as A and another control signal as B, the output, the combined logic of these two transistors can be given as AND, A and B, right? A and B. That means whenever you connect NMOS in series, this is nothing but the AND operation, right? See, whenever you're connecting NMOS in series means it is corresponding to AND operation. For example, if I have 3 NMOS in series, and let me make the control signal as A, B, C, right? If that is the case, then the output is gonna be A and B and C, right? So when you want to implement the AND operation, you have to make the NMOS in series, right? You have to put the NMOS in series, which will typically look like this. The pull down network, you will have transistors in series like this, right? So when you call this as A and this as B, means whatever you are getting will be A and B. And one more thing you have to keep in mind is this is inverting by default. Okay, that means all the complementary CMOS circuit you will get the output in the inverted form only. So this is inverted by default. Anyway, you have implemented the AND logic. This is how you are implementing the AND logic. So when you are connecting two NMOS in series, let us say M1 and M2 in series, means you are implementing the AND logic. That you have to keep in mind. Okay, right. Why it is AND logic? Is there any reason behind it? Yes. Okay, so say when you are having different NMOS in series, why it is implementing AND logic? Okay, see, let me make it A and B and C and D and E. That is, the output is gonna be A and B and C and D and E, right? That is the output. And these are all control signals to the gate terminals, right? To the gate terminal. You know that only when you apply 1 to the gate terminal, the NMOS will be on. This I have discussed a few videos before. Only when you apply 1 to the gate terminal, the NMOS will be on. This I have discussed a lot, right? So here you know that when Y will become 1 with respect to AND, when you are ANDing the different variables, when Y will become 1, only when all the inputs are 1, right? There is only one case in which Y can become 1. That is when all the inputs are logic high. When all the inputs are 1 means the output will also be 1 when you take AND operation. That's the same thing is being implemented here. As you can see here, all the things to be 1, then only whatever we are giving here, let us say X, that will be passed to the output, right? That will be passed by the transistor towards output. Okay, if let's say C is not 1, C is, let us say it is 0, right, then this transistor will be off, right? So whatever we are transmitting, it cannot get passed through this transistor because it is off. So what you will be getting is just 0, right? It's just 0 what you will be getting, nothing else, right? So that is why it implements AND operation. Okay, that is why I'm saying that when you connect NMOS transistors in series, it is gonna form AND gate. Okay, similar AND operation. That's it. Okay, so NMOS in series makes AND gate, right? Makes AND operation, right? Like something like this. Not gate. It is not a gate. It is operation. That's it. AND operation. Okay. Alright, we know that pull-up network, which will contain only PMOS, is nothing but the dual to NMOS, right? I told you pull-up network and pull-down network are dual to each other. Okay, so pull-up network, which is nothing but the PMOS, dual to this, which means that whatever you are drawing in parallel, you have to, whatever you are drawing in series, you have to draw in parallel. That's it. That means in pull-up network, when you make two transistors to be in parallel, that will implement AND operation. Okay, that will implement AND operation. See, in pull down network, which you use only NMOS, when you make transistors in series, that will implement AND operation, right? Similarly, since PMOS is dual to NMOS, whatever is there in series will become parallel here, right? That is the duality. Whatever is there in series, that will become parallel, which means that if you are connecting in series means it will become parallel. That is the duality. So when you connect two PMOS to be in parallel, that will implement AND logic. Okay, that will implement AND logic, right? Similarly, when you have NMOS in parallel, that will implement OR logic. Something like this. This is the parallel structure, right? Something like this. Okay, let us say this is A and this is B, right? So output will be A or B, right? Okay, and PMOS, when you draw in pull-up network, I told you this is just a dual. So whenever you are having something in parallel means that will become series. In PMOS, when you connect two PMOS in series, that will become OR operation. Right? So the output will be A or B, right? So understand that when you connect two NMOS transistors in parallel, that will become OR operation. And since in PMOS you are taking the dual, you are just making the conversion from parallel to serial. So when you connect two PMOS transistors in series, that will become OR operation. Okay, so having these things in mind, let us draw the CMOS NAND gate. Okay, so CMOS NAND gate is what I'm gonna draw. Okay, so the logic is very simple. Y equal to A and B, the whole bar. Okay, that means NAND means you first use the AND operation, then you put a whole bar, that is NAND gate. The truth table will look like this. When you make both as 0, you will get to 1. When you make 1 as 0, you will again get 1. When you make 1 as 0, you will again get 1. When you make both 1 means you will get 0, because this is NAND operation. In AND gate you will get 0 0 0 1, and if you simply complement it, it will become 1 1 1 0. That is the result of the NAND operation. Take the AND and complement it. That is how it looks like. Okay, and understand one thing, guys. When you are designing CMOS technology, when you are using CMOS technology, the output will always be inverted, right? So there is no need to think of NAND first. The output will always be inverted. So just implement this logic, A and B. That's it. The output will always be inverted. Not a problem. Okay. So how to implement this? Y equal to A and B, the whole bar. First you design the pull down network. I told you when two inputs are there, right? There are two inputs. So they are in AND operation, right? So this is an AND operation and the whole complemented. Right, so first of all, let me implement AND operation by connecting two NMOS transistors in series. I told you when you connect two NMOS transistors in series, that will create AND operation, right? That will create AND operation. So let me do that. Okay, I have to connect like this, to ground this, and this will become A and this will become B. Okay, and this is the pull down network, okay, which will contain only NMOS transistors. I again told you that it should contain both pull down network as well as pull up network. How to draw the pull up network? Pull up network will contain only PMOS, and PMOS, all the PMOS are dual to NMOS. Okay, all the PMOS are dual to NMOS. So whatever is being series here, that will become parallel, right? So the inputs A and B are to transistors M1 and M2, let us say, both are in series. So let me draw two transistors in parallel and give the same input. That's it. Input must be same. Okay, I told you inputs must remain same. Again, if I want to go back here, you can see that all the inputs will remain the same. Only thing is you have to draw it with respect to the duality. That means series will become parallel, parallel will become series, right? So the here M1 and M2 are in series, so I am drawing it parallel here. Now if I name the transistor M3 and M4, they are in parallel, whereas M1 and M2 are in series. So this is the pull up network, and the output must be taken here. This is the output node. Okay, so this is nothing but 2 input NAND gate, 2 input NAND gate. That's it, 2 input NAND gate. Fine. So now let us try to analyze this. So there is only one case where you will get 0. That is when you make both as 1. So the output is by default it is A and B, the whole bar. So whatever is there and A and B only. So that is the whole bar. That's it. Because it's complemented, that's why it's complementary CMOS. So when you make both as 1, you should get the output as 0. That is the idea, right? So I'm making both as 1. I'm making both the inputs have being 1, right? See, when you are giving 1 to the PMOS means PMOS will be turned off. This is a very basic idea which I told you before. When you are giving 1 to the PMOS means PMOS will be turned off. So both the PMOS will be turned off. There is no way you can pull up the output. Okay, both the PMOS will be turned off means this is the VDD line. This is the 5 volt line, right? Both the PMOS is turned off, so you cannot pull up the output. There is no connection here. You cannot make the output to go to 1, logic 1. Here when you give 1, the same 1 to the NMOS, both the NMOS will be on. So there is a direct connection to ground. When you make both the transistor are on means it is shorted, so there is a direct connection to ground. So the output will be 0. Output will be 0 because there is a direct connection from the output node to ground. Okay, if PMOS is on means there will be a direct connection from the output to the VDD line, that is the 5 volt line. In that case the output will become logic 1, but in this case, since we are applying both 1, the NMOS will be active and the output will become 0 since the output is grounded. So hence proved, when you apply 1 1 you are getting 0. So that's how you can take some examples like this. Thanks a lot.